Welcome to physics class on motion in a plane, uniform circular motion, part 3. Now in this topic we will try to discuss about the circular motion first, and then we will come to uniform circular motion, and in it we will try to find out that of the expression relation between what linear velocity and angular velocity, and we will also try to find out that of the angular acceleration. So let's see what are the topics to be discussed. Okay, in it, let's see. Here, as I told you, that we will try to discuss about the circular motion, then to come to that of angular acceleration and all, we need to know what is meant by angular displacement, angular velocity, time period. Then we will lastly go to that of uniform circular motion. Now, what is this circular motion? It is a movement of an object along the circumference of a circle or rotation along a circular path. It can be uniform with constant angular rate of rotation and constant speed, or also non-uniform with changing rate of rotation. Here we do not mean about that of the uniform circular motion, we simply mean only circular motion. So if it is a circular motion, then the body should move along the circumference of a circle or rotation along a circular path. Okay, it can be uniform or it may be also non-uniform, okay, with a changing rate of rotation. Now see here, it is the some example, okay, that you can have. It is of that of merry-go-round, okay, like this. Or if you take a stone and tie it onto a rope, and if you reel it, then the motion of that stone, that will be also in a circular path. Your rotation of the planets around the sun is also one of the circular motion. So these are all circular motions. Now let's see what is meant by angular displacement. While learning about these rotational motions or circular motion, we need to take the analogy. That means the similarity between that linear motion and rotational motion. When we talk about that of linear displacement, it is nothing but it is the displacement. Means what? It is the shortest line drawn from the initial to the final point, right? So we call it that as linear displacement. Here we need to take the difference of that of the final angular angles described by the body to the initial angle. Okay, so that is known as what? Angular displacement. So angular displacement is defined as the angle through which an object moves on a circular path during a given interval of time. For example, if an object at the very beginning, okay, it takes from here to here, that means during the time t, the body has described, okay, if the body moves like this in this circular path, then the angle described by the body at this very beginning time t is equal to t, let's take it, that angle is nothing but that angle is denoted by theta 1. Okay, so after moving, okay, for some time at an angle, say let's take it as at a time t is equal to t plus dt. So I'm drawing in a very magnified way. So the time interval from here to here, we take it as a small time dt. So during this interval of time, small time dt, the angle described, okay, by the body from this position to this position, okay, that means the angle described is what? From the very beginning, that means we have taken this as a reference axis, okay, from here to here, it is what? Theta 2. So how much angle has been described during this interval, time interval dt, is from where to where? From here to here. This is the angle. So that angle, okay, can be obtained by nothing but by just taking the difference of this final angle described, okay, with that of the initial angle, okay, angle described. So this difference of the angle described by the body during this interval of time, we call it that as what? Angular displacement during this interval of time. Got it? Yes, in the example here also it is given that theta 1 is equal to 1 radian, theta 2 is given as 5 radian. So angular displacement delta theta, okay, we call it this as delta theta. This will be equal to what? Theta 2 by theta 2 minus theta 1. That means 5 radian minus 1 radian. That will be equal to what? 4 radian. Okay, that is what it is having. So this 4 radian, we call it this as angular displacement. So it will be given here also just like that. It is the angle, okay, its SI unit is in radian between the initial and the final positions. So it is the angle of it is a difference in angle, I should say, between the final position and the initial position. It is what it is given here, okay. So your angle described can be also expressed as what? Theta, this theta is equal to what? Theta will be equal to what? S divided by R, where R is the radius and S is nothing but this is the circumference or the arc length, you can say. Not circumference, rather it is not for the whole circle, but this is for this arc length. We take it this arc length as theta, R as the radius, and this theta is nothing but your theta will be equal to what? Theta 2 minus theta 1. This will be the theta, okay. So from here to here, that is denoted by theta 2 minus theta 1, okay. So during this, what happened? You will have that angle, your circumference C is equal to twice pi R, right? That expression is coming none other than from this expression. Theta is equal to arc length divided by radius. So if the arc length is for a whole circle, then this will be equal to what? C R, okay. This arc length will be equal to the circumference, radius will be there, no doubt, but this theta will be for the whole, okay, rotation. Then the angle described by the arc length will be what? Twice pi. So from where this C is equal to coming to be twice pi R? It is coming from here only. Got it? From here. So your C will be equal to twice pi R. That means if you cross multiply it, then you will get it this one. C is equal to twice pi R. So by using that relation also, you can find it out this one as theta is equal to what? Theta is equal to S by R, where S is the arc length and R is the radius of the circle. So this arc length is nothing but, if the body move along like this is the nothing but this is the distance traveled by the body during that interval of time, okay, dt. Got it? If it's t is equal to t, as I said, and here if it is equal to t is equal to t plus dt, then the time interval to move by the body from this position, okay, to come up to this position, it will take the time small t. How do you get it? T plus dt, final time minus initial time, so you will get it what? dt. Got it? That is the interval of time, right? Let's see others, okay. Angular velocity. Angular velocity, it is similar to that of the linear velocity, okay. So here also we need to find it out. What? When we say linear velocity, then we say that rate of change of displacement. Here also same thing. Rate of change of angular displacement will be equal to what? Angular velocity. It is a quantitative expression, okay. It is a quantitative expression of the amount of rotation that a spinning object undergoes per unit time. See, per unit time is there, okay. If it is velocity, then rate of change of angular displacement in the linear motion, right? So likewise here also, in the case of angular velocity, it will be rate of what? Change of what? Angular displacement, okay, we call it that as what? Angular velocity. When we say rate, the denominator should be time, okay, so that means amount of rotation of a spinning object per unit time, okay, we call it that as angular velocity. Now it is a vector quantity consisting of angular speed, okay, component and either of the two defined direction or senses. That means it will be having the magnitude as well as what? The direction also, because it is a vector quantity. Got it? Now let's see. So if an object, okay, if an object at a position, at the very initial position, if the object is here at t is equal to 0 and the angle described by the body after the interval of time, say small t, okay, after interval of time small t, then the body from here it moves like this and it reaches up to this position. So the time interval, final time minus initial time, that will be time taken is how much? T only. So during this small t, time small t, what happened? The angle described by the body at the center of this circular part, it will be equal to what? Theta. It is given here as theta. So this is the angle described. Got it? So what happened? Your angular displacement, rate of angular displacement, your angular displacement is theta, okay, so rate of change of angular displacement means what? Angle described divided by the time interval, this one t, that will be equal to nothing but this will be equal to the angular velocity denoted by omega, okay, this angular velocity is denoted by omega and it is a vector quantity as we have said, okay. Yes. Now time period. Time period is a time taken to complete, okay, by the body moving along the circular path for one complete rotation, okay. So the time taken to complete by a rotating body or a moving okay, along a circular path to complete one complete cycle or complete rotation, we call it that as what? Time period, okay. So time taken to complete by a particle, okay, by a particle of one rotation, we call it that time as what? Time period. And frequency means what? It is a number of complete such cycle in a unit time, okay, we call it that as what? Frequency. So number of complete rotation by the particle in one unit time, okay, is called as frequency. Your unit time is taken as 1 second, so we may define frequency as what? Number of complete rotation, okay, in 1 second, we call it that as what? Frequency. Got it? Frequency, right? And frequency is denoted by nu. This nu is not v, okay, this nu is not v, rather it will be in the form of like this, like v but little bit upward like this. You better write in this way, okay, or you can simply write like this also, but this one is little bit longer. See, if you write it like this only simply, then it looks not nice, okay, it seems to be small v, but if you pull up little bit like this longer, then we have to be understood that this is nu, not small v, okay. This is not a Greek letter, not an English letter, rather a Greek letter, okay. So this will represent frequency of that circular motion, okay. Now let's see about the relation between angular velocity and time. If d theta, okay, be the angular displacement made by the particle in time dt, that means as we have taken in that circular path, so okay, like this, if this is a reference axis will be the x-axis only, we generally take it as x-axis, okay. So during the time small time dt, if the angle described by that rotating body from here to here, okay, if it is d theta, then what happened? Your angular velocity will be defined as d theta divided by dt. Got it? That is what it is mean. Now its unit is radian per second. We know it that angle described is measured in terms of radian and time in seconds, so it will be radian per second, okay. And now for one complete rotation, the angle swept by the radius vector is 360 degree or twice pi. For complete cycle, what happened, the angle described will be what, 360 degree, or you can write in terms of radian as twice pi radian. Then the angular velocity is what? Angular velocity is nothing but that will be what, theta divided by t. Here theta will be, for the whole complete rotation, it will be 360 degree or twice pi, and this time will be nothing but your time period. Time period means for one complete time taken for one complete rotation or revolution, we call it that as time period, right? So, and it is denoted by capital T. So this time taken for one complete cycle, it will be what, denoted by capital T, and it is given here theta as what, twice pi, and t, small t, by capital T, that means the time period. Okay, so if the particle makes n revolution per second, means your frequency nu will be what, n. Frequency nu, okay, this frequency will be nothing but this is what, it will be n per second, means what, n divided number of revolution, okay, number of complete revolution is what, n, so it will be equal to n. Okay, so what happened, this twice pi into 1 by t, okay, that will be equal to what, this 1 by t will be equal to, either you can use it nu or you can use it n also, no doubt, as it is a number of rotation per second. This n, I mean this n is nothing but this will be frequency, so you can replace it this t by nu, so that what happened, your omega will be what, twice pi nu, like that. Okay, yes, it is given here as twice pi n, as I told you that nu and n are same, okay, here in this, because this is the n revolution per second is given here, so instead of nu you will get it as what, twice pi n, where n is equal to 1 by t. Okay, where n represents what, this is number of revolution per second, or you can express it this number of revolution per second as frequency also. Got it? Like this. Clear? Yes. Now this is the relation between the angular velocity and the time. Let's see. Let PQ is equal to ds be the arc length covered by the particle moving along the circle. Then the angular displacement, okay, d theta is expressed as d theta is equal to ds by r, from where it is taken, s is equal to what, your s is equal, let me write like this, s is equal to r theta, where s is the arc length, okay, r is the radius, and theta is nothing but this is the angle subtended by the arc length, okay, and this theta, it is the angle subtended by the arc length at the center. Okay, so if we use this relation that I told you, that your circumference will be equal to what, twice pi r, theta will be what, twice pi, and radius will be r, so your circumference is equal to twice pi r. It is coming from here, arc length, okay, will be equal to radius times the angle subtended by the arc at the center. From that relation we are coming. Okay, so now if it is in that way, your d theta will be equal to ds by r. This is a small angular displacement, d theta, okay, this is a small angular displacement, okay, and this, during that small angular displacement, what happened, your arc length will be small, so we denoted that arc length as ds, where r is a radius. But for that of uniform circular motion, we can take it that what, your s, distance travel, is equal to velocity into time. If v is uniform, then we can take it that what, distance travel is equal to velocity into time. But for us, the distance travel is very small, so we take it as ds, velocity as v, and time, during that small time dt, angle described is also small, the distance travel, that means your arc length will be also small, okay, this arc length, but your arc length can be expressed as what, linear velocity into time by using this. From where we are using this, because your v is what, uniform, okay, If it is uniform, then we can use this relation, distance traveled is equal to velocity into time. But if your velocity is not uniform, then we can't take it that one. But here v means what? Uniform speed, okay, not uniform velocity, rather this will be uniform speed, because in the circular motion direction keep on changing. So that constant amount of velocity, or rather you can say speed, it can be expressed in this way: ds is equal to v into dt. Then what happened in this diagram? You see, let's take it that the particle, okay, or the body that is having that rotational motion, rather uniform, what with a uniform speed, okay, along a circular path. Now let's take it that this is the initial point P, and from P to move up to Q, it takes what? A small time dt. During this small time dt, the circular path length, okay, the circular path length, that means we will take it this as the arc length. This pq is nothing but this pq will be equal to what? This pq, let me write it as arc length. This is nothing but this will be equal to your ds, okay, and r is the radius, no doubt. Angle described during the small time dt. Arc length will be also small, okay, this arc length will be also small, and so the angle described, or angular displacement, that will be also small. Got it? So we express it as in that form by using that s is equal to r theta, or you can write it as what? Theta is equal to s by r. So by using this relation, the first one, I mean, we have this first relation. And when the body is moving with a uniform velocity or constant velocity in a particular direction, then the distance described, okay, or the distance traveled, we can find it out simply by using that velocity into time. So as the body is moving with a uniform velocity, okay, rather with a constant speed, I should say, okay, that velocity is along in this direction, but magnitude will be same, okay, magnitude will be same here also. This v, this all will be having with the same uniform speed. So we can define this pq as ds into velocity into time, or rather not velocity, I'm sorry, this should be speed, okay, speed into time. Why I am saying speed? Because this body is moving with a uniform motion along the circular path. Uniform motion means what? It will be having what? Having the same speed, okay, that same speed. Velocity at this point will be along this direction, along a tangent. At this point it will be also along a tangent. So the direction of velocity will keep on changing, but the magnitude of the velocity, we call it that as speed. So speed will be remaining constant, that we call it as uniform speed. So that uniform speed is here. Got it? ds is equal to v into dt, like that. Clear? Yes. Let's take it another diagram so as to make you more understand. Okay, now let's take it that ds is equal to v into dt, as I said here, this one, okay, it is here. So what happened? Your d theta, okay, can be expressed as what? You try to replace this ds here only. Got it? Then what happened? Your d theta will be equal to v dt, okay, v dt, okay, this one by r. Or if you try to bring this dt downward like this, then it will be d theta by dt. You will get it like this. So what remains on the right hand side is v by r. Okay, what is this d theta by dt? This is nothing but this is the angular velocity. So angular velocity we will denote it by what? Omega. So your omega will be equal to what? V by r. V by r. Got it? So your omega will be equal to v by r, or rather you can express this as what? V will be equal to omega r if you cross multiply it like this. So this is a relation between what? Linear velocity, okay, and the angular velocity. You can express it, okay. So your linear velocity will be equal to omega times r. In the vector notation, you can write it this as v vector is equal to omega times r vector, like this. Got it? that is what we are having here. Okay, this is what we are having here, like this. In the vector notation, what happened? Your v will be equal to omega vector cross r vector. Got it? Yes. Now we are coming to that of uniform circular motion. Before, up till this, what happened? We were considering about that of any circular motion, but this one is mainly of that of uniform circular motion. How do we define this uniform circular motion? If a body moves along a circular path with a constant speed, then we call it that as uniform circular motion, which is also an accelerated motion. Why an accelerated motion? Because its direction of the velocity keep on changing continuously. Okay, so as direction changes, what happen? Direction of what? Direction of speed changes, then we will say that velocity changes. So if velocity is changing, then we say that rate of change of velocity, we call it that as acceleration, is not it? So if velocity changes, there will be acceleration, and so uniform circular motion is an accelerated motion. Okay, now this is an example, okay, of that of uniform circular motion. But actually, if you take it this as a sun, okay, if you take it this as a sun, and the one which is revolving here, the spherical one, blue one, if it is taken as a planet, then to some fair approximation we can take it this as a uniform circular motion. But if you go in higher studies, it will not be a circular motion. The planet do not move with a constant speed, okay, and the planet also do not move in a circular motion around the sun, rather it moves in an elliptical path, okay, with the sun at one of its focus, right? Now then what happened if when I take it that as a what ellipse, as in this shape, your focus will not be at the center, rather it will be somewhere here. Okay, the position of the sun will be here. So what happened when the planet comes closer like this here? So what happened? It will move faster. When it is farther away somewhere here, it will move slow. Okay, when it is here closer toward the sun, then it will move faster. Got it? When it is farther away, it is moving slow. So what happened? That means as the speed is not constant, we cannot take it that the motion of the planet around the sun as uniform circular motion in a real sense. But for our learning up to our standard here, we can take it that to a fair approximation that the planet moves around the sun in a uniform circular motion. Got it? And moreover, actually the path is not circular in the case of the motion of the planet, rather this is an elliptical motion. But as it is a very vast one, okay, a very big one, of whose radius is very large, okay, we can take it to some fair approximation that for our studying as what? Circular motion. Got it? Yes. Let's see angular acceleration. Angular acceleration is nothing but it is the rate of change of angular velocity. When we define linear acceleration, we define as rate of change of velocity simply. Velocity there means linear velocity. So in the case of rotational motion also, your angular acceleration is nothing but this is the rate of change of angular velocity. Okay, and its SI unit is what? Radian per second square. Okay, and it is denoted by alpha. Okay, this is not an English letter, rather it is what? A Greek letter, and alpha means it is written like this. Okay, yes. So let's see. Now we know that this angle described by the body, okay, that will be given by what? This angle described is what? Theta, right? And we know that angular velocity v and the linear velocity, it is related with this like this, or rather you can express it as v is equal to omega r like this. So if you want to denote it angular acceleration, then it will be what? D omega by dt. Okay, if you want to express your linear acceleration, then we write it like this: rate of change of linear velocity. So in the case of angular velocity, if it is alpha, then this will be d by dt of what? Rate of change of what? Angular velocity. Got it? So that is what it is written here, right? So your alpha is nothing but this is what? Rate of change of angular acceleration. Angular velocity. Angular acceleration is equal to what? Rate of change of angular velocity. Now this is very important part about the relation between the angular acceleration and the linear acceleration. Okay. Now linear acceleration is equal to what? A rate of change of linear velocity. A is equal to dv by dt, as we have just said. So in the case of this rotational motion, the relation between linear velocity and angular velocity, that is what? Linear velocity and angular velocity v. Okay, it can be related. We have just said that v is equal to r omega, right? Now then what happened? Therefore your acceleration is equal to what? Dv by dt. Okay, dv by dt. From here this v, okay, your a, this can be expressed as d by dt of v, like this we can write it. So if you use this v as from this relation, v is equal to r omega, then it will be d by dt of what? R omega. That is what it is doing here. Okay, so r being constant, wherever the position of the particle along its circular path, the radius will remain same throughout. So r is a constant. So you take this r outside the differentiation and you try to differentiate this omega. So this what? D omega by dt is nothing but this is what? Your what? Angular acceleration, which is denoted by alpha. That is what it is here. So your a will be equal to, linear acceleration will be equal to r times what? Angular acceleration. It is just very easy to remember. If you want to correlate with linear velocity and angular velocity, a factor r is coming there. So linear velocity will be equal to r times angular velocity. Your linear acceleration will be equal to what? R times what? Your angular acceleration. Okay, like that you can remember it in a very easy way. Now in vector form you can write as what? Alpha vector cross r vector. In the case of linear what? Velocity and angular velocity, there also you correlate this like this, no? In the same way here also, if you want to correlate with that of this what? Your linear acceleration, your linear acceleration in the vector notation, you can write it a vector is equal to what? Your omega. No, alpha first. You need to write it alpha cross alpha vector cross r vector, like that. Okay, there in the case of linear velocity also you write it as what? Omega vector cross r vector, right? Like that. Same thing here also. Okay, but while writing you better write it this v as v is equal to, you can write no doubt with r omega, but you better write omega r. V is equal to omega r, a is equal to what? Alpha r, like this. So that while writing your cross product in the vector notation, okay, it will be at this same order. That will be both better. Okay, not with r omega. You try to read as v is equal to omega r, so that in the vector notation it will be equal to, v vector will be equal to omega vector cross r vector. Here in acceleration also, acceleration vector will be equal to, okay, angular acceleration vector alpha vector cross r vector. You can remember in that way. Okay, now next is the last part of this centripetal acceleration, and this is very important. Okay, here in the centripetal acceleration is nothing but this, as the body is moving with a constant speed in a circular path. I told you that the direction of the velocity keep on changing, and if it is keep on changing its direction, then velocity changes. If it is velocity changing, then we will say that the motion is an accelerated motion. And if it is an accelerated motion, then how do we find that expression of what? Angular acceleration? That is the thing that we are going to do. And if your accelerated angular acceleration is a vector quantity, then at what direction it will be pointing? We will try to find it out, that one. So let's see that here your average velocity, when we try to find out average velocity, then we take it that change in velocity to the change in time. Okay, Suppose if your body P is the body is at this position P at time, say suppose t is equal to small t. After some small interval of time, say let's take it that t is equal to t plus dt. Okay, t plus dt. This difference in time, okay, this, let's take it this as the initial time. Let me denote it by ti. Okay, ti, and this as tf. Okay, so your time interval delta t will be denoted by what? Tf minus ti. That means t plus dt minus small t, that will be nothing but it will be dt. So when I write this delta t, that is nothing but the difference. When I write this small dt, that means this is the small change in time, we call it that as dt. This is what? Difference in time. It may be very big or small, doesn't matter, difference of time. But this one dt is a small time dt, or rather you can say small increment in time, or rather small change in time. So as I'm drawing very in a very magnified way, actually your p and p prime, okay, p and p prime are very close to each other. Let's take it in that way, so that the angle described by the particle, okay, from p to p prime, to move from p to p prime, okay, along this path, let's take it that the angle described by the particle, let's take it as what? Delta theta. Okay, so what happened if you want to find out this delta v, small change in velocity to the small change in time, then we need to take it this expression first. Now let's take it that, okay, h and I. Now before going to that, let me explain you first. Okay, now at this point P, okay, its linear velocity, okay, at this point, as the body is moving in a circular path like this, what happened? The particle at this point, okay, will have the velocity along its tangent like this, as the body is moving like this. So along that tangent, okay, the velocity will be directing here like this. Let's take it that as v. Now at this final point, we are taking this as the initial point and this as the final point. Okay, at this final point also, the direction of the velocity, as even though they are having the same magnitude, let's take it that the direction are different. Okay, so this will be also along its tangent, and moreover the magnitude will be same, but let's take it that the velocity here as v prime like this. Okay, so as the direction changes from v to v prime, we will also say that the velocity changes. Okay, because your velocity can be changed either by magnitude or by direction or by both. Okay, so what happened during this change in the velocity from v to v prime, what happened? The direction, okay, changes, and so the angular displacement also changes as delta theta. Now if we redraw it this, okay, then it can be drawn in this way. Here see this v, okay, it can be drawn here like this. Okay, the velocity at this initial time, we can replace it by what? Gh vector, and that of the velocity, okay, v prime at the final time, that can be replaced by this gi. Okay, this will represent what? V, gh, and your gi will represent what? Your v prime, as it is also written there. So now the change in velocity, from v to v prime will be denoted by this line. Okay, by this line. Okay, this is from where we have taken this from that of triangle law of vector addition. Got it? So this your hi will be representing what? Your hi will representing nothing but delta v. So your hi, okay, this hi will represent nothing but this will represent your delta v vector. Okay, delta v vector like this, or rather let me write it. somewhere here above, so that your hi, okay, your hi will be equal to what? Delta v vector, like this. Got it? And this is nothing but this is a change in velocity in the time delta t. Okay, as I told you that here, let's take it as a time t here, and here as t plus dt. So as we are talking about not small change in time, rather you can take it a big time also as delta t, so that the difference in time will be what? Delta t. So during that delta t, what happened? The change in velocity is denoted by hi, and it will be expressed as what? Delta v vector, like this. And the direction is here, you see, in this direction. Whatever the direction here, we have taken here. Whatever the direction here, v prime, we have taken here. So this change in the angle, okay, or rather angle described, that will be also equal to here. Why? Because this line and this line are perpendicular, being tangent, okay. When the perpendicular changes by an angle of delta theta, naturally this radius will also change by delta theta. So that much angle change by this delta, by this radius to come up to here, that is delta theta. Same thing here from B to this one, the angle described will be also what? Delta theta here. Got it? That is what we are talking about. So what happened? Your hi, as I said, hi will be equal to what? Delta v, and this is the change in velocity in time delta t. So your, therefore we can also write your delta v vector will be nothing but this is what? V prime vector minus v vector, okay. That this is a change in velocity. Now from where this is coming? Actually it is coming from that of the vector notation v, okay, v plus delta v, okay, as they are taken in order, and this one is taken in opposite order. So from your triangle law of vector addition, v prime, v plus delta v will be equal to v prime, v plus delta v, okay. If it is in the vector quantity, then it will be what? V prime vector, like this. So your delta v from this relation, your delta v will be equal to what? V prime minus v, like this. That is what I'm writing here, okay. Clear? Now let's take it a triangle PC, okay, PC P prime, and that of triangle what? G I and H. These two triangles are similar. Why? Because this radius is also equal to this radius, right? So this is an isosceles triangle, and the angle between them is delta theta. And here also in this case of this triangle GHI, this V prime and V are of equal magnitude. The only thing is what? They are moving with a different direction, okay. Magnitude are same. As I told you that in the case of uniform circular motion, speed remains same, direction only changes. So the magnitude of this velocity we call it as speed, magnitude of this velocity v prime also we call it as speed. So speed remains same. So the length of these two, which will represent the speed of this vector quantity v and v prime, okay, these two will have same length, same magnitude, I mean. So what happened? The angle described between them is also what? Delta theta. So what happened? By that axiom known as what? Side angle side, these two triangles are similar. That means what happened? Your triangle, which triangle? Let me write here as PCP prime, okay. P here, C here, P prime. This will be similar to triangle what? HGI. HGI. So angle between them is what? This angle G. Angle between them is what? C. So what happened? This PC will be equal to what? Your C P prime. Both are of radius, okay. Both are of same radius, length of same radius. And here also in the case of this what? HGI also, this is V prime and this is B. So B and B prime are of same length, So what happened? You will have that in a two similar triangle, then what happened? The ratio of their corresponding sides are equal, is not it? So from that two triangles, that is what this, let me write it again here as triangle what? Triangle PCP prime is similar to triangle what? HGI, right? So the ratio of their corresponding side is what? Delta V divided by V. This will be equal to PP prime. Let me write here, okay, and I will remove it again. So this is what? Your delta V by V, okay. Delta V, what is this delta V? Your HI, okay. This HI will be equal to what? Your HI divided by V. V is what? This one, okay. And in this case also, onto this what? Left hand side triangle, that means PCP prime, your corresponding side for delta V will be what? PP prime, and corresponding side for this GH will be nothing but it will be PC. So that PC is denoted by R, so I am writing here as R, okay. So from this relation again, but we will have that arc length, okay. Arc length is what? Your PP prime. PP prime, that means this distance, okay. This distance is equal to what? As the body is moving with a uniform motion, that means it will be equal to distance travel is equal to velocity into time, right? V into delta t. Got it? So what happened if we use it, that PP prime here, the relation, then your relation will be what? Delta V by V. I'm coming from here, okay, from this relation. So delta V by V will be equal to what? Instead of PP prime, you can express as what? V delta T divided by R. So from this relation, if you try to simplify that delta V, you try to bring this delta T in this side toward the left hand side, so that it will be what? Delta V by delta T. And if you take it this V to this side, then it will be what? V square by R. So what is this delta V by delta T here? This is nothing but this is a rate of change of velocity. What type of rate of change of velocity? Rate of change of angular velocity in one sense, okay. This is a velocity, change in velocity. So we call it this what? As average acceleration, okay. That average acceleration, or rather your linear acceleration, this is equal to what? You can write it in the last step as like this. Your acceleration A, okay, from here you can come here. Your A will be equal to what? V square by R. What is this A? This is A is nothing but this is the average one, okay. So we can write it that as average here. It is here. Average acceleration is equal to what? V square by R. Got it? But what is this V? As I told you that we have done up to here, okay, that A is equal to V square by R. Now we also know that your linear velocity can be expressed as what? What? R omega, or omega R you can write, okay. So if it is V square, then this will be also like this. Got it? And V square by R, I'm doing this one. So V square by R means what? V square means R square omega square by R. So 1 R and R will cancel. What remain is what? R omega square. So your acceleration will be again equal to what? R omega square. You can write as V A is equal to V square by R, or R omega square, like this, where we know that omega is equal to what? Twice pi by T, okay. We know that omega is equal to twice pi by T. Again, T 1 by T is equal to what? Nu. So you can replace this omega as twice pi what? Nu, like this. So if you want to express this as in terms of frequency, then it will be what? Twice pi whole square nu square. Okay, it will be coming up there. Got it? So another r is there. So if you use it, this expression omega is equal to what? Twice pi nu. Here in this, okay, then what happened? You will get the expression as it is given here. Your a will be equal to what? Your a will be equal to what? 4 pi square nu square r. Got it? So this is the expression of what? The average acceleration. Okay, and if you want to express it this in terms of what? Linear velocity, then you can use it, this relation, as I told you. If you want to express this linear acceleration with that of angular velocity, then you can use this relation. Got it? But I'm telling you that whatever we have done here in this, what happened, this direction also here, this direction also here. So your change in velocity, that means delta v, okay, it is directing in what direction? It is directing along hi, right? So your acceleration is directing toward the center of the circular motion, or the circular path, I should say. Okay, so your acceleration is directing toward the center of the circular path, and we said that acceleration as centripetal acceleration toward the center. So if you want to find it out, that centripetal force, then we know that mass, okay, force, centripetal force is equal to what? Mass into acceleration. So mass means the mass of that body, okay, which is experiencing that circular motion. Then we can write it as what? mv square by r. This is a relation for that of the centripetal acceleration. We know it, right? So you can use this acceleration to find out your centripetal acceleration in terms of linear velocity, in terms of angular velocity, in terms of what? Frequency also. You can find it out in that way. Got it? So those are the things to be discussed, as I have written here also. Okay, so with that, okay, we come to the recapitulation part. Let's see. I will just make it in a very quick manner so that you can also see it. If you want to see it very clearly, then you can pause this video and you can watch it. Okay, this we have already done in the explanation part. Okay, these are all those things that I have just told you now in the acceleration, about that acceleration, okay, that is given coming here. Okay, yes, with this we will come to the end of our today's topic, okay, or class. Thank you for watching.